Hi, today we will talk about a theory of everything, and I will start with a pure mathematical remark. Is this a well-defined problem? In other words, if we talk about a theory of everything, do we really know what we are talking about?
What we are talking about when talking about a theory of everything. It is not as obvious as you might think. Richard Feynman once mocked the concept, saying that the theory of everything is already there. The all-encompassing equation exists. It is U equals 0. Don't you believe? U equals 0 stands for the sum over all ui, and each ui is defined as the quadratic deviation from the known laws of physics, such as Newton's second law or Einstein's famous formula. Not convinced?
We will come back why you're not convinced, but since this is also a video about science communication, I think it's not a bad idea if we try to define what we're talking about. I love, by the way, the irony of David Lindley.
There is no way to know in advance what this theory of everything will look like, but most physicists like to think when they see it they will recognize it. But be honest, if someone shows up with a theory of everything, would you recognize? Would you really like to talk about? Would you listen? Would you even want to know about? The problem of discussing a theory of everything is not so much about evaluating the correctness of calculations or deciding that something is in agreement with observations, but that the approaches are so different that it is hard to find common ground where even to start.
That's what I'm trying to do. I will guide you through a series of 5 statements you can agree or disagree with. I hope that everyone will agree on the first one, but they become increasingly controversial. I will argue that all statements are correct, but if at a certain point you don't want to follow any longer, that's okay. At least we will know better what we are talking about. Here's my first statement.
Physics has achieved something based on fundamental insights. Thus, to evaluate possible future insights, we should analyze the achievements of the past.
That's what I would call evidence-based.
We use cell phones because 150 years ago, someone was curious about electromagnetic waves. We take pictures because in 1905, Einstein understood how light releases electrons from metals, and his theory of relativity is the reason why you know where you are using your GPS. Since we are interested in fundamental theories, let's go a little bit deeper here and consider the sensational discovery of electromagnetic waves by Heinrich Hertz in 1886. It boils down to a very simple formula. The electric and magnetic constants epsilon naught and mu naught are related to the speed of light c. That means light is an electromagnetic wave from a methodological perspective. However, this equation reduces the number of constants from 3 to 2, one constant less. Let us then consider the example of Johann Jacob Balmer, who in 1885 discovered a formula that explained a variety of spectral lines with just one number called Rydberg's constant, a tremendous simplification. And some 30 years later, Niels Bohr expressed Rydberg's constant by other constants of nature, again, one constant less. I would claim that this is epistemological progress of quantum mechanics, but you may have an objection here. Hey, don't we need Schrödinger's equation for quantum mechanics? Or Maxwell's theory of electrodynamics for C? Yes, we need sophisticated math to justify these simplifications. It could be vector analysis for Maxwell's theory, or Hilbert spaces in quantum mechanics, or even differential geometry.
But at the end of the day, it is important that you have less arbitrary numbers that describe reality.
Progress is done when you have a constant of nature explained, which brings us directly to our second statement.
In the past, progress was related to reducing the number of natural constants. The less unexplained numbers, the closer we are to a theory of everything.
If you expect that these statements are far from mainstream physics, I must disappoint you. A lot of people agree here. The less fundamental constants we have, the more we have understood. Yes. Not to mention Albert Einstein, who favored an extrapolation of the above statements. A satisfactory theory of reality must do without any arbitrary numbers. He said,
I cannot imagine a reasonable unified theory containing an explicit number which the whim of the creator could just as easily have chosen differently. Let us take, however, an even broader perspective and think about how intellectual progress is linked to a simplification. Great thinkers such as Galileo Galilei from Pisa have closely observed falling objects.
But Galilei measured actually the acceleration is just a nice legion, but he did perform some experiments here.
There is an almost infinite amount of data of how objects behave under the influence of gravity. However, all these trajectories, well, almost all, eventually boiled down to one single value, local gravity. That means, in an abstract way, it is a simplification, and at the core of scientific understanding. And the lack of simplicity probably disturbed you in Feynman's fake formula U equals 0. Understanding numbers is the job of a theoretical physicist. Now Newton comes along, wonders about this number, and explains it with an even more general formula, a formula that holds for more than 90,000 objects in the solar system. Quite a simplification. Let us consider also the influence of visionary ideas which are not primarily mathematical. Newton's observation earthly and celestial motion had the same origin. Bohr's flash of genius that Planck's constant could be seen as angular momentum of the electron orbiting the nucleus.
It seems that fundamental progress has often three ingredients: a visionary idea, a mathematical formalism that justifies it, and at the end, a simplification that explained arbitrary numbers. Let me back this argument with another deep thinker, the philosopher Thomas Kuhn.
Thomas Kuhn, in his landmark book, The Structure of Scientific Revolutions, introduced the concept of normal science, a period in which unexpected results called anomalies accumulate. These anomalies are integrated in the existing paradigm, that is, the accepted theories, which become more complicated, however. Scientific revolutions instead introduce radical simplifications called paradigm shifts. Such revolutions are often explanations of constants of nature. On the other hand, a newly discovered constant may be called an anomaly. To get rid of these anomalies is the essence of theoretical understanding.
So I hope you agree that it is the job of a theoretical physicist to explain constants of nature, but maybe you're not immediately happy with my third statement.
As a matter of principle, most constants of nature can be eliminated.
You may raise a couple of objections here, such as what is a constant of nature, or that we can get rid of them easily, but keep in mind, as Einstein said,
numbers arbitrarily chosen by God do not exist. Their alleged existence relies on our incomplete understanding.
By the way, I don't blame you if you disagree with some ideas how to calculate constants of nature, but at least we must try it.
Let us try to shortcut what could be discussed endlessly. What is a constant of nature? We may simply assume any observational data, since these condense into a few numbers once we have understood the laws.
People have tried to count the number of fundamental constants, and I will not enter this debate here, if it is 6, 19, 31 or whatever number. Let us agree that we must calculate and explain these numbers if we want to make progress. Otherwise, just forget about the theory of everything and everything what you have heard about.
Let us consider a list of constants, following more or less a chronological order of their discovery: the speed of light c, the gravitational constant g, Planck's quantum of action, the fine structure constant 1/137, proton-electron mass ratio 1836, the proton mass, the proton radius, and considering cosmology, also the radius and mass of the universe. In case you miss something, such as the elementary charge, keep in mind that it may be included in the definition of the fine structure constant. Thus we are talking about independent constants that are not explained by others so far.
Now this is of course not complete, and I do not even claim these are the most important ones, but we can safely say that without calculating those, you hardly get anywhere. One of my favorite anecdotes is about two young physicists approaching Paul Dirac.
Mr. Dirac! Mr. Dirac! We have a new theory! Listen to us for a minute!
Can you calculate the fine structure constant? Well, come back when you have done it. But also Richard Feynman said, it's one of the greatest damn mysteries of physics. All good theoretical physicists put this number up on their wall and worry about it.
Let's be clear. I'm not saying a theory of everything is an easy thing, but as a matter of principle, it is thinkable that one day we might be able to calculate these numbers.
Someone may worry also about the mass of the muon,
tau on.
W and Z bosons, or even the entries of the Kabibel-Kobayashi-Moskauer matrix. Indeed, there are a lot of parameters nature seems to provide us with.
I admit that I have my opinions about the standard model, and maybe sometimes I have been too controversial in my publications. Here, let me just say, if you want to calculate all these numbers, I wish you good luck with that. And before you accuse me that I'm not able to calculate these constants, let me just grab one example and show how such a calculation could look like.
The bold hypothesis, for example, is that the gravitational potential of the entire universe equals c squared. This idea goes back to Erwin Schrödinger and was later developed by Dennis Sciama, while the visionary idea of the origin of gravity being related to the masses in the universe is due to the Viennese philosopher Ernst Mach.
Just to be clear, I do not claim this is the correct formulation, but I insist that if we want to make progress, we have to eliminate also the gravitational constant g. Otherwise, you believe in a kind of god of modernity called Big G.
Some people claim that dimensionful quantities such as g have no meaning and we can set it to unity or use the Planck length or whatever. This is wrong. Yes, one could write it with other numerals. Yes, you could express g using feet and pounds. But physically, you would feel if big G had the double amount. Its numerical value is a meaningful message of nature.
Not for nothing, physicists have made great efforts to determine the gravitational constant Big G. Not the first experiment, but the sophisticated one involved this 6-ton sphere of lead. It would certainly be a revolutionary insight if one proved such a formula.
Now let us fast forward a little bit and just summarize that there are ideas such as Dirac's large number hypothesis, how to get rid of other numbers, but if you find them unconvincing, just try something else.
What I am trying to do here is discussing a best case scenario of what might possibly happen if we were incredibly smart and figure out all these numbers.
One thing you will notice is that every constant bears certain physical dimensions or units, and we can get rid of some of them, such as condensing the electric stuff into the fine structure constant. Or, this is an ingenious idea of Julian Barber describing masses by inverse accelerations, seconds squared per meter instead of kilograms. This would kind of automatically implement Newton's third law. Let us assume this is possible. Interestingly, the units of Planck's constant would then be not kilogram times square meters per second, but just meters times second. Let us again assume you have a flash of genius and you can calculate the mass and radius of elementary particles using constants of nature, of course justified by a mathematical apparatus yet to be developed.
But however smart we may be, there remains one problem, which is my fourth statement.
H and C cannot be eliminated. Their existence is an anomaly related to the fact that we use space and time. You will never explain Planck's constant with the units meters times seconds and the speed of light, meters per second, because there are simply no constants left which one could put into a reasonable formula that produces these units.
One may express the same fact by using Planck's units, which I don't like very much because I think they are a playground for non-falsifiable theories, but this is another issue. Anyway, you can combine constants of nature such as G, C and H and produce the units of meters in second. In other words, if you want to define proper scales by fundamental constants in a world consisting of space and time, you need C and H. But we don't want them.
Even more obviously, the definitions of meters and seconds are human conventions. There is nothing to calculate. Thus the question remains, why do H and C exist at all?
Why do we need time and length scales at all? Because a long time ago someone called Isaac Newton used space and time to describe physical reality.
Space and time are two concepts Newton postulated without any further justification. Within Newton's theory, based on space and time, there is no reason whatsoever why masses should not be accelerated beyond a certain velocity. The existence of such a limiting velocity c, hence, is an anomaly. Moreover, within classical physics, there is no reason whatsoever why angular momentum should be quantized. Thus, the very existence of h poses a problem for space and time.
Inevitably, this leads us to our fifth statement.
For a fully satisfactory description of reality, space and time must be abandoned and replaced by another mathematical structure.
This is a statement hard to digest, and if you're still here, thanks for your patience. You might ask at this point what I have to offer as an alternative for space and time, but to be historically fair, everything has been said a long time ago.
Quaternions are fundamental building block of the universe. This was the conviction of William Hamilton, the famous Irish mathematician who discovered this four-dimensional number system while walking along the Royal Canal in Dublin 1843. Mathematicians commemorate this event every October 16th, yet the significance of this generalization of complex numbers seems to be underestimated in physics.
Now, why should space and time be replaced by quaternions? I will give you a couple of arguments, all of them quite intuitive and none of them worked out in a rigid sense, but I think they are quite interesting to the least.
First of all, we need to explain why nature presents itself in such a peculiar 3 plus 1-dimensional spacetime structure. It is intriguing, therefore, that quaternion algebra naturally singles out one real dimension and 3 complex ones. Obviously, this is what particularly fascinated Hamilton. The conventional concept of a 4-dimensional spacetime, by the way, strongly advocated by Hermann Minkowski in 1908, glosses over this fundamental problem while ignoring the necessity of explaining the existence of c. Even Einstein's theory of relativity, however elegantly makes use of the speed of light, it does not explain the very existence of such a limiting velocity. And however successful quantum mechanics is, it never justified the constant that had given birth to her, the quantum of action h.
Maybe not coincidentally, physicists have struggled without success to unify quantum theory and relativity. It seems that the problem is ill-posed, however. We need to worry about space and time in the first place and explain the constants h and c.
Furthermore, quantum mechanics and electrodynamics teach us that both complex numbers and vectors are mathematical tools we need to describe nature. It turns out that quaternions encompass both of them. Maxwell had even formulated his theory using quaternions. Particularly intriguing objects are quaternions of unit length, which are mathematically equivalent to well-known structures such as complex matrices or the 3-dimensional unit sphere. There are a couple of remarkable properties we should know.
And this is where eventually I show you two ideas which are not very old.
A truly satisfactory description of reality must explain the appearance of c and h from purely mathematical principles. Quaternions offer such a unique property, non-commutativity.
Here's an example. Unit quaternions are very similar to rotations in 3-dimensional space. And here, A times B is not the same as B times A. Non-commutativity is a key feature of operators in quantum theory, such as angular momentum, with the unit h. So my first proposition is
Planck's constant h is a consequence of the non-commutativity of quaternions.
what remains to be explained is the constant c, and again there is a specific property of unit quaternions in this case.
Almost all equations in physics involve differentials, a concept that needs to be redefined in manifolds such as the S3. S3 is called a Lie group, and unlike usual functions which remain the same type of function when taking the derivative of a Lie group becomes something qualitatively different, a Lie algebra. As a visualization for non-experts, you may imagine that an element of a Lie group is a point on the sphere, while an element of the algebra is a vector in the tangent space. Keep in mind that this picture is only two-dimensional.
If you try to find a space-time analog to such a tangent space, it is clear that the light cone is a good candidate, something intimately related to c. Thus my second proposition is
the speed of light c is a consequence of the fact that S3 is a Lie group with a tangent space.
There are a couple of other interesting things to mention here, such as spin and double cover, or SO4 in electrodynamics, but in order not to go beyond the scope of this discussion, I stop here. If you want to explore the properties of unit quaternions in an intuitive way, I highly recommend the visualizations by Ben Eater. Really fantastic. I hope this video helped you a little bit to understand what we're talking about when talking about a theory of everything. And the take-home message is we must consider constants of nature, and probably we have to abandon the concepts of space and time. Thanks for watching. If you enjoyed the video, give it a thumbs up, and if you're interested in fundamental questions of physics, subscribe to this channel.